Okay, so okay, hope you are able to see. You are able to see the screen.
Yes, sir.
Okay, okay. So just to recall, okay, let me just yeah. Uh, Yeah, so just to recall, we have as a part of large scale machine learning, we have first discuss. So basically, the topic we are covering is how to do machine learning faster. Okay, especially if your data is large. So if your scale of learning is large, how can we do machine learning faster? Okay, so we have covered in this regard. Okay, stochastic gradient descent. Can anyone tell what stochastic gradient descent achieves? What is the advantage of stochastic gradient descent? Okay, so let me tell then. So stochastic gradient descent, basically what it achieves is, if you see, it sort of it tries to it achieves lower training time, right? How does it achieve lower training time? It achieves lower training time by using um, so lower time for update, lower time for parameter update, and this is much lower, right? Okay, so so this is what it achieves. Okay, so it achieves lower time for parameter update, and there are many reasons. So so one is that the entire data. So the main reason is that the entire data set has not you need not have to go through the entire data set. So what this in order to update the parameter. Okay, so you can just go for a mini batch of data in order to update the parameter. Okay, and still the algorithm ensures that at the end of it you are converging towards the global optimum of the actual objective function. Okay, so that is the advantage, or that is the achievement of stochastic gradient descent. Okay, okay, and then we have discussed acceleration techniques. Acceleration techniques for optimization. I think somebody is unmuted. So unless you have something to say, please mute. Because yeah, there is noise. Okay. Yeah, so we have seen a lot of different acceleration techniques. Again, what is the advantage here? That any update, either SGD update or some other update, any update. So basically, let me put it this way, that reduce the number of updates. Okay, so that is the advantage here. Okay, or that is the objective here. Okay, so this can be applied to so in traditional optimization it was used for gradient descent or other kinds of updates. Now it is used for it is also used for stochastic gradient descent type updates, and there are two broad class of tricks that we saw and combinations of that, which is one is momentum kind of tricks, other one is adaptive gradient or gradient scaling kind of tricks. Okay, so uh, okay, so this is the second topic. Okay, And the third topic we have covered is ADMM, right? So, so what does ADMM achieve? Okay, so it achieves distributed optimization. Okay. Okay, so distributed optimization or faster distributed optimization mainly by lowering communication. Okay, lower communication. Okay, and how does it achieve this? So what it does is, instead of if your objective function is the form where it is distributed onto some m computers. Okay, instead of for every update, okay, to the parameters, instead of taking let's say gradient from each of the computers and then adding them up and doing the update, what it is doing is it is doing some kind of local optimization on the subset of the functions or data that you have on each of these computers, and then it is trying to synchronize or arrive at a consensus after the local optimal with the local optimal parameter. Okay, so that is so then the total number of updates reduces dramatically. Okay, or total number of cross computer communication reduces dramatically. Okay. Um, so up till now, this is what we have discussed. Okay. So let us get into batch normalization. Okay. So yeah, so this is the reference. I have given the reference in the end. Okay. So what is batch normalization? Okay. So just to answer, so it is a technique which is primarily applicable. So it's not a general technique. It is a technique which is applicable to deep learning architectures. Okay. So for other types of optimization problems, this may not be useful. This is not useful. Okay. So this is specifically designed for deep neural networks. Okay. Okay. So now, so what is the problem, right? So the problem is, so we all know, we all know that, there are features, right? So any machine learning algorithm takes features. Okay. So consider, for example, that you are taking a family. Okay. And you are trying to predict, so what kind of house can this family buy or something like this. And you can have like features like whether the family has kids or not. So this is a 0-1 feature. Okay. And what is the value of the car that this family has? Okay, so is it $500 or is it $100 or something? I mean, like I'm just saying, these are some example features. Okay, now, so in this, so you can see, and then based on this, we may try to recommend a particular house to this family. Okay, so they want to buy maybe a certain kind of house. Okay, now you think that this feature. Okay, so it is in the hundreds. Okay, so its value is in the hundreds, whereas this feature, okay, its value is just 0 and 1. So there are 2 orders of magnitude difference between the values of these features. Okay. So now you think that suppose you want to compute, now you want to use these features in a machine learning algorithm. Okay. So you may want to compute distances, or you may want to compute there are so many things that you can do, right? In order to use these features into a machine learning, you can do dot products. Okay, You can multiply by matrix, so you can do linear transformation. You can do nonlinear transformation as is done by each layer in a neural network. OK, so all of this can be done. OK, now depending on the on the transformation. OK, just the range of the value that this feature has affects how well you can learn. OK, so for example, I mean, I'm just saying, let's call this feature F1, let's call this feature F2. And suppose I want to do a sigmoid of, let's say W1 times F1 plus W2 times F2. OK, and this is my Y or something like this, let's say. OK. OK, so you see this is in the range just 0 and 1. OK, this feature is in the range hundreds. OK, so this feature is going to have very, very little effect on this thing unless your W2 is roughly 100 size value as W1. OK, so if that is the case, so that thing can happen, but that thing has to be learned, and that learning takes time. OK. OK, so typically what people do is people do what is called a feature scaling. OK, so again, feature scaling basically, so I will tell what feature scaling is, but what feature scaling does is it does two things. OK, one is so mind you that theoretically you need not you would not have to do this kind of feature scaling. OK, because your model is general enough. OK, that even if you give unscaled features, it should work. OK, but in practice, people do feature scaling all the time, and people see that things only work when you do feature scaling. OK, so why is this the case? OK, so there are two things. One is that people have seen that the optimization algorithm, gradient descent, stochastic gradient descent, whatever, converges faster if you do feature scaling. OK, so this is number one. Number two is that there are less number of numerical instability. So there is at times you may have to do matrix inversion. OK, or some this kind of numerical computation. Sometimes you have to do softmax computation. OK, in all these cases, there are numerical instabilities which come. OK, I am not going into detail of that. You can just look up. OK, so these numerical instabilities are also less if you do feature scaling. OK. OK, so so feature scaling is really, I mean, it's thought of as a hack. OK, so there are two very common feature scalings that are done. OK, first one is it's sometimes called linear scaling. OK, it's just that you scale the data such that all features, OK, lie in the range 0 to 1. So this is without loss of generality. OK, you can use any range. So we are just using the range 0 to 1. OK, but the thing is that it is linear. So your final feature value, this x new, is a linear function of the feature value x. OK, so this is number one. OK, and basically you are just dividing by x max minus x min. So you have to go through the data set for each feature. You have to find x max and x min, and then you have to do two passes and you have to do this computation. OK, so this is number one. Another kind of feature scaling, also sometimes called whitening, which is done is that it is made zero mean. OK, zero mean and unit variance. OK, so the feature actually does not lie in a particular range. OK, but the values of the features are such that across the data set, across the training data set, its mean is 0. OK, and its variance is 1. OK, so these are the two types of feature scaling that are done, and it is not clear which one performs better, which one performs worse, but I mean, one advantage of the second type of scaling is that you are not, so there are advantages and disadvantages. The advantage of first one is that your value is always going to lie between 0 and 1. Okay, so there is no uncertainty there. Okay, the advantage of second type is that you are not constraining the values to lie within a range. So if there is really a large, there are some outliers or some large really deviated data points, okay, those will be allowed, so those will not be affected, they will really be outliers, they will be outside the range, okay, and you can focus on the main data point. Okay, so yeah, so this is the general idea. Okay, so okay, so now I mean, so you can also do this in a batch way. So actually batch normalization, if you think about it, it is not a new concept. So it was done also in the old times. Okay. Uh, and basically, instead of doing this in a for the entire training data set, you can also do it for a batch of training data. Okay, so you can do this kind of feature scaling for a batch of training data also. Okay, so okay, so what are the advantages we are seeking to achieve? We are seeking to achieve lower training times because of lower covariate shift and less exploding and vanishing gradients. So as you know, exploding and vanishing gradients is basically it's a numerical instability. Okay, we will discuss what covariate shift is. Okay, so or maybe I can describe this. So covariate shift. Okay, so let me actually describe using this particular figure. Okay, so you see, you look at this B plot. Okay, so what this is plotting is the activation of a particular neuron. Okay, or I think it is of yeah, a randomly selected neuron. Okay, so one particular neuron. Okay, over the training iterations. Okay, so now oh, oh, okay. Yeah. Okay. So, and I think the top line is the maximum, and the bottom line is the okay. Yeah. So the top line is the 15th percentile, and bottom line is the 85th percentile. But it doesn't matter. So you can think of this as how the activation varies throughout the training. Okay. Now you see, this activation is first decreasing, then increasing, then decreasing, and so forth. Okay, this particular activation. Okay. What does this do? So if you recall your back propagation algorithm, okay, or if you recall, yeah, so your activation is multiplied by the incoming back propagation signal. Okay, in order to compute the signal which is further propagated back. Okay, so you see the activation actually controls the value of the gradient for this particular signal or this particular neuron, and whichever neurons are, or whichever weights are, so you can think of the network like this. So suppose this is one particular activation. So whichever are the incoming, whichever are the incoming signals basically coming to this, these all have weights, right? So W1, W2 till, so this is for the kth layer, let's say for the kth layer, WK1, WK2 till WKN, let's say. Okay. So this activation affects the update of all these guys. Okay. And now this is like fluctuating so much. Okay. So sometimes it is getting updated in negative direction, then again positive direction, then again negative direction. Okay, so 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 this is the problem. Okay, so this is called the covariate shift. Okay, so and this is happening parallelly, as you can understand, for millions of activations. So each layer may have like at least tens of thousands of activation, and for each of these activations, okay, it is affecting all the parameters that contribute to it. Okay, so this is the problem. Okay, of the covariate shift. Okay, so that these covariates are actually shifting a lot during the training. Okay, uh, okay. Another thing is that so this is kind of debated that batch normalization also sometimes reduces the demand for regularization, especially if you see dropout is a very popular method for regularizing deep neural networks. Okay. Now, dropout, the problem is that, as you all know, that I mean, if you don't know what dropout happens is, what happens in dropout is that you suppress the signals from randomly selected neurons. Okay, so this is what you do. Okay, so what happens is that your training takes more time. So you can just check. So if you run any neural network without dropout, it may overfit, but it will train fast. Okay, so the training loss will go down very fast. The moment you add dropout, the training is slower. Okay, that is because some activations are, it depends on the rate of the dropout and all those things, but basically some activations are not being considered for a particular iteration. So given an iteration, some activation will be, suppressed. Okay, so those activations will not contribute towards the training. Okay, so that further causes slowness in training. Okay, and if you use batch normalization, there is a claim that you may use lesser dropout. Okay, so you may still have to use dropout. So it does not say that it will not overfit, but you may use a lesser dropout, and then that further increases your training speed. So as it is, batch normalization increases the training speed because of less covariate shift, okay, and more numerical stability. Furthermore, you may be allowed to use a lower dropout if at all. Okay. 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 Yeah. The third point is, of course, because you have lower danger of exploding and vanishing gradient, so you can use higher learning rates. Typically, if you try with higher learning rates, your training may still converge. Okay. Uh, Yeah, and yeah, so the fourth point is that, yeah, so sometimes you see saturation in certain part of the network, like all the thing happens that all the activations go to zero. So that may also sometimes be mitigated. Okay, but the main point here being that your covariate shift uh, gets reduced. Okay, so that is, I mean, at least that is what. So there have been counter claims also, but the consensus right now is that batch normalization improves training performance because it reduces covariate shift, which is what we just discussed. Okay, so okay, so here is an example of how batch normalization works. Okay, so this blue is the test accuracy of, I think it was an MNIST network. Okay, and yeah, so you can see that it is already, it's starting much higher, and also it is sort of climbing faster and reaching, it's much faster. It reaches the actual accuracy much faster than so this is, I think, the number of updates. So you can see that even after 40,000 updates, still the network without the batch normalization is not doing too well. Okay, so it is faster. Okay, so now let us think about the normalization using Gaussian that we discussed. Okay. Now, how will you do a batch normalization? So the naive method is that you take the output. So you take a mini batch. Okay. You take the output of that particular mini batch. Okay. You compute the mean. Okay. You compute the variance. Okay. Then you just normalize. Let's say, I'm just assuming that we are trying to do this x minus mu, okay, by sigma, this kind of normalization. Okay, so x hat, let's say, so this normalized the normalized activation x is going to be this. Okay. So by the way, I hope for all of you the connection between feature and activation is clear. Okay, so features you can think so let me see this. Yeah, so you can think of if this is the input feature. Okay, the output of this hidden layer is actually input feature to this last layer. Okay, so this is clear, right? So essentially batch normalization, what it does is it aims to do feature normalization, okay, but for each of the layers of the deep neural network. Okay, so it will do, so whichever layer you want to normalize, it will do. Okay, so not just at the input level, but also hidden level or also at higher layer levels, because these are actually nothing, the activations of higher layers, okay, are nothing but input features to the next layer. Okay, so it is like feature normalization at this layer. Okay, so I hope this particular thing is clear. Okay. Okay, so now if you want to do this, okay, and you can just compute the mu batch. Okay, you can compute the mu batch and sigma batch. Okay, and you can compute this, and this can be batch normalization. So the question is, why does it not work? And the reason this does not work is that you see your mini batch is kind of a random thing. Okay, and so this transformation. Okay, let me put it this way, that this transformation is changing with every mini batch. Okay, because mu b and sigma b is changing, and there is no logic whatsoever why this transformation should converge to something, because your mini batches are constantly changing, because you're doing random selection, a selection of random examples, and you are presenting them. Okay, so this is number one. Moreover, this constantly changing transformation is, so even if the transform, let's say, so there is a transformation that is happening. Okay, so you are taking this x, okay, at each layer you are applying some transformation t to this x, whatever the transformation be, and you are getting x hat. Okay, so first thing is that this transformation is changing, but even if the transformation was not changing, okay, still what is happening when you are back propagating, okay, you are not sort of taking this transformation into account. Okay, so your back propagation is just working as though there is no transformation. Okay, or there is so that is the problem. Okay, with the naive implementation of the batch normalization. So is the problem clear? Okay, so I think this slide I will is not discussed. So what is the solution? Okay, so the solution is very simple. Okay, the solution is that you introduce a new batch normalization layer. Okay, which is we know that the transformation is a linear transformation. So basically, your transformed activation Y is going to be your input activation. Let's say X, okay, and then it's going to be multiplied by some constant gamma, okay, and it's going to be so there is the multiplicative constant and there is the additive constant, right? So this is the most general form of linear transform, okay. So this is what batch normalization layer does, okay. So it takes as input X, K, okay. It somehow computes this X hat K, okay, and then it I will tell you what this X hat K is, okay, and then it computes YK, okay, which is just this transform of XK, okay. Now what they did is they said that look, this transformation, this gamma and beta are also learnable parameters. Okay, so here you can see or if your original network is something like that, this is the modified network where you have added batch normalization to the hidden layer. Okay, so what is happening is your whatever your hidden layer output was, okay, so this is your hidden layer output, remember? Yeah. So earlier, this output was directly going to all of these layers, all of these neurons, okay, of the next layer. Now what is happening is that you are computing this transformed output, which is YK. So this is XK. Okay. This is YK. Okay. This transformed output is YK. Okay. This transformed output is being computed, which is like this. Okay. Which means that here there is a one-to-one connection and each connection has one parameter. So there is a gamma 1 here, beta 1 here, gamma 2 here, beta 2 here, and gamma 3 here, beta 3 here. Okay. So this is what your parameters look like. So parameters, number of parameters is of the order of number of activations, unlike fully connected layer where it's square of that, right? So it's number of neurons in the previous layer times the number of neurons in the next layer. So here it is nothing like that. Okay, so there is not too much overhead added in terms of the parameters. Okay. Okay. Now, and this is the output. Okay. So now how do we compute this X hat? Okay. So, okay, yeah, so this is I think this we have already discussed. Okay. Okay. So the question is, how do I compute this X hat? Okay. So this is how you compute the X hat. Okay. So you first compute. So your input is you have this mini batch of examples of size, let's say M. Okay. And then what do you have to what does the batch norm layer have? It has this set of parameters to be learned, okay, gamma and beta, okay, and you have the yeah, you have also the output, which is Y. Okay, now you compute the mu b, the mean of this particular mini batch, okay, and the variance of this particular mini batch. Okay, then this X hat, okay, is the usual normalized, okay, or whitened version of X. Okay, so you do the whitening here. Okay, so you do the whitening. Okay, then you apply this transformation, linear transformation on the whitened input to get this Y. Okay, and then basically you can think of something like this, that this gamma, okay, is somehow maintaining this 1 by, rather it's somehow maintaining this sigma b, right? So if the sigma for all the mini batches were the same, okay, then this gamma is somehow maintaining sigma, okay. I mean, so it's not exactly maintaining sigma. You have to understand this, that if your y output was expected to be x, okay, so if your y output was expected to be x, it may be that, you know, a slightly so like covariate shift reduced output is better. Yeah. But we should give it the option that it should be able to remember x. So if your you know, if your sort of this mu b, okay, was mu b and sigma b was same for all the mini batches, okay, then your gamma would somehow learn this sigma, okay, and your beta would somehow learn this minus of mu b by sigma b. Okay, ignore this epsilon. This epsilon is just to you know, for not having divide by zero error, because if your sigma can be zero also. Okay, so okay, but it's essentially like x minus mu b by sigma b. Okay. Okay, so so this is what batch normalization does. Okay, so just to understand the entire algorithm, so at the time of training, I think it is pretty clear what you do. Okay, at the time of testing, what you do is you compute this mu, instead of mu b, now you compute the mu batch, or at the time of testing or deployment, okay, you compute this expectation of x on all the layers, okay, and also variance of x on all the layers, okay, and then this is your transformation. So you have gamma and beta, but additionally uh, uh, you compute this variance and expectation, and this is basically your transformation. Okay. And I mean, you can understand that this is what this is basically sort of compensating for the training time. So this is basically doing like whatever transformation at the training time happened to X at the test time, the same kind of transformation should happen. Okay. Yeah. So I think this is the crux of the thing. Okay. You can look at the details of the algorithm, but yeah. So yeah, needless to mention that you have these extra set of parameters now, which are this gamma and beta. Okay, and this is for each batch norm layer. So each layer will have a separate set of gamma and beta. Okay. Okay. Yeah. Yeah. So I think this is just the population stats. Yeah. So some so basically how just to conclude. Okay. So this is all about how you can. So what does batch normalization do? Okay. So batch normalization accelerates training of deep neural networks without doing much, without compromising on the accuracy. In fact, yeah, so that is the idea. Okay, so it should accelerate the training of deep neural networks without compromising on the accuracy. Okay, and how does it operate? So as a user of the batch normalization, what you can do, if you think that a particular, so you can add batch normalization to all outputs. Okay, but remember that batch normalization is actually adding extra computation. So for each batch normalization layer, okay, this much of extra computation has to be done. Okay, So you have to take a, you have to make a choice, okay, that whichever layers you think are suffering from the most covariate shift. Okay, you can also try to measure the covariate shift. Okay, you can add batch normalization layers to those layers. Okay, okay, and if you do that, okay, uh, you will see that your training will become faster and much smoother. Okay, so you can then try experimenting with higher learning rate. You can remove dropout. Okay, yeah, you can reduce, if you are doing L2 regularization, you can again reduce the weight on L2 regularization. Okay, you can also accelerate learning rate decay. So if you are using 1 by t times kind of decay of learning rate, you can accelerate it, like you can say 1 by 2t or something like this. Okay, or even sometimes you can change the exponent here. Okay, so these things you can do. And uh, overall, this gives you kind of a tool to do faster training of neural networks. Okay, deep neural networks. Okay, so this is the original paper. This was in ICML 2015. Okay, and this particular page is where the slide is, and there are some more references. If you search, you can see many blog articles and all, and there are some such references also in here. Okay, but this is the basic reference. Okay. Okay. So any questions? Um, okay, let me see. Okay, so here at least there are no questions. Okay, so yeah, so anybody has any questions? Okay, so Monday there is a test. So I know there are some questions. So I think okay. So let me first stop the recording.